So, hello. Thanks for coming to my talk. I'll be presenting ETL, which stands for Extract, Transform, and Load, and kind of how I came to a conclusion that it's the dirty little secret of data science. So I'll explain what I mean by that throughout the talk. So I come from the Children's Hospital in Philadelphia, Pennsylvania. And the hospital is split into kind of two components. We have the Research Institute, which I work on, sorry about that, and the hospital itself. And so I have the privilege of working on a team of very smart people, and I get to work with clinicians and researchers who are at the top of their field in their respective areas. So I'm going to just give a brief introduction to extract, transform, and load, and kind of what that means. It's very simple. It's just a process. So it's kind of an abstract process. There are many implementations of ETL processes, and I'm not going to be getting into the details of those because it's very much specific to your requirements of data and the domain in general. So very simply, for those who aren't kind of familiar, who might not do ETL often, you can very simply think of it as kind of mapping data from sources and targets, sources to targets through various transformations. And again, the complexity of those is kind of up in the air. One thing I do want to harp on a little bit is that for anybody who comes from domains or industries that have very complex data, you need to have domain knowledge of the data in order to be effective at writing ETL. Any kind of trivial transformation, such as taking data that's structured in a relational database, turning it into, putting into a MongoDB collection, that's trivial. That's not, frankly, that interesting to me personally, and that really doesn't require too much understanding of the domain. So what I will be kind of speaking about today is much more complicated ETL, and so just to have some context. So what is domain knowledge exactly? It's understanding the assumptions, the constraints, and the underlying semantics, the meaning of that data in a particular context. So regarding the data science bit, I saw this on Hacker News, which was a nice comment, and I've talked to various data scientists, and they always complain about how much data preparation they have to do all the time, which I can concur with that. And so I enjoy this quote that basically, if you don't have knowledge of the domain, you're not going to be very effective at doing any kind of analysis to the data that you're working with. So to give a quick example of what I mean by domain knowledge, on the left here is data, real data extracted from our medical record system. And this happens to be pretty simple data, frankly. You can see that it's delimited by semicolons, but the thing that you have to understand is that the right-hand image is what researchers and clinicians need to see. And if you kind of take a look at those rows of data, and you can kind of see, maybe I see the numbers, I see the scale of it, okay, I kind of get it, but there are a lot of assumptions and kind of various things you have to know about that data to be able to turn it into this nice image. And this is an audiogram, it's called, and this basically is an image that audiologists use to assess hearing loss of their patients. So we'll look at this a little bit more in a bit. So today's talk is going to kind of cover three main areas. I'm going to explain the challenges of my particular environment within a hospital and research context. I'm going to discuss an approach to modeling domain knowledge. So again, I wanted to harp on that a little bit because that's kind of the crux of this talk. And I'm going to show and introduce an implementation of the approach that I'm discussing. All right, so let's talk about my environment a little bit. So CHOP, which we refer to it as because Children's Hospital Philadelphia, has a listing on their page that they offer 98 various specialties and services. Okay, so it's a very big hospital. There's 10,000 plus employees at this hospital and research institute, but it's a very big institution. So the kinds of data that we work with, that I get to work with daily, depending on the different kinds of projects that I'm focused on, can include anything from clinical data right from the medical record system, imaging data such as radiology and the impressions that go with them, whole genome and whole exome data. So there's a big push right now in healthcare to integrate whole exome or whole genome sequencing into everyday practice. And so as a side note, my team has a privilege of trying to figure out how to develop that workflow in pediatrics, and we're trying to develop a model for other pediatric hospitals to use in their institutions. We deal with biospecimen data, so blood, tissue samples, things like that, and then just everyday general study-specific data. So this could be something as simple as a researcher collecting survey responses from families or patients. So we kind of have this whole diversity of data that we get to work with, and any given research question may tap into any one of these areas, if not all of them. So for those who aren't familiar with clinical systems, aside from durability and making sure data is not lost, the number one kind of design goal of clinical systems, specifically I'm referring to kind of a medical record system which acts as a data warehouse for most all of the data. It's flexibility. Flexibility is the big thing, and as you can see with the 98 various specialties and services that are offered, you can imagine this data warehouse has to be quite flexible to facilitate all of those needs. So in our particular case, every specialty in the hospital gets its own data model. So they have teams of the clinicians who are kind of the heads of their departments. They get together and they say, okay, we need these various data elements as part of our data model because this is going to help us capture the correct data, and it's also going to facilitate our workflow and our needs. So that's the first thing. The other thing is that patient care changes all the time. So these groups of people get together and they determine what they need, and then they say, oh wait, I forgot something, or oh wait, we changed our practice and we changed our workflow, or some new device that they use bedside, they realize that they have to now capture that data in this medical record system. From a government standpoint, we have new vocabularies and new standards being integrated all the time. So one big change that's occurring right now, and most other countries have done this already for years, is that we're transitioning, for those who know ICD-9 billing diagnosis codes, we are transitioning to ICD-10 codes, which is basically a 100-fold increase of the number of billing codes that a doctor will be able to enter into this system. So those things get integrated, and we have to map concepts, we have to map these data in order to integrate those. And the other fact that is relatively recent, also like I mentioned, is that we get whole new data types. So hospitals never had to deal with genetic data before. Maybe SNPs and certain variant data, but not whole genome and whole exome. That's a whole different kind of scale that hospitals have not had to deal with thus far. And so integrating that as part of the medical record system and kind of hooking it all together and seeing how it means is a challenge in and of itself. So I'm not a huge fan of the term big data because I think everybody has their own interpretation of it, and I think it's effectively meaningless. I think it's very much dependent on your needs of that data, and I am not going to claim that our team deals with terabytes of data like Twitter or the big services out there. But what I deal with all the time is what I consider deep data or wide data. The breadth of data that we have to tap into is just very large, and I would argue is much larger than most other industries out there, just because of the vastness of it. So size is one thing, scale is one thing, but we have the breadth that we have to be able to work with. Okay, so that's my environment. That's what that's my playground. So it's fun, but there are those challenges. So I'm going to kind of muse a little bit about the approach of trying to better manage that and trying to integrate it better into our workflow so that we can manage all that domain knowledge as we kind of work on all these individual projects. Because frankly, it's too difficult when you work on a project for 6 months and you go to another project for another 6 months, and then you have to do a data refresh or something from a project 6 months or a year ago, and things have changed in the meantime. It's very hard and challenging to kind of keep up with all of that because of there's just so much context that you have to maintain. So at the time that I was thinking about this, I was kind of musing about this, I was at the time writing some ETL, naturally, and I was working on the second revision of a project that I've worked on for a number of years regarding the audiology, as I spoke about. And this, we are working with 2 other institutions and integrating their data into a public resource of audiology data that's de-identified, that's available on the web. You can sign up for it, and if you're an audiologist, if you want interesting data, you can sign up for it and look at it. So I was doing ETL. At the same time, I was learning about graph databases. I was reading the graph databases book that the authors of Neo4j developed, that O'Reilly published. And so I was thinking about graphs. And then at the same time, I had a project kind of make me think about data provenance. And I will go into more detail of what that actually means in a second. But data provenance is something that a lot of people don't think about, but they kind of use all the time, but they might not know it or understand it as formally. So just to give you some context of what I was thinking about. So ETL is a black box to everybody except for the person who wrote the ETL. That is another claim that I would like to make. It is especially true when you're trying to communicate what needs to happen to a researcher's data or clinician's data in order to get into a format for them to actually do research on. So as I mentioned and showed, the data that was in the medical record system there, that is to most people just not usable data. They can't, there's no types, it's just strings of text. They can't really work with it that well. And so the magic of ETL is being able to restructure it and put it into a structure that is actually useful and that you can actually use programmatically as opposed to just parsing out strings and things like that. You can compute on the actual integers and the values and the numbers that exist in that. So ETL is a black box. My goal is trying to uncover that, make it more transparent, at least within our team, so that if I talk to one of my team members, they can at least understand what I was thinking at the time, what I was doing, and making it just easier for everybody to understand over time. So I can also look back at it later and understand what I did. Okay, so the first thing we need to do when we kind of deconstruct ETL, as the example here, is thinking about the components. So if we go back to this data here, we can see that that's just the column header at the top, just so people have some context. So in this particular case, we have 4 rows, and this is composed of represents one audiogram effectively. So the first line represents the header of the columns, as you can kind of infer. The rest of it are the values in those columns. Some are empty. If some people notice that there's a 60M in there, well, for those who are not audiologists who don't know this data model, you're not going to understand what that means. And those are flags. Those are Boolean flags. That's what that means. And that actually means that masking was applied. So in the case of the second row here, the left ear was being tested for air conduction, and the other ear was masked. So there was a cover over the other ear so that the left ear could be correctly tested. So if you didn't know that, you wouldn't know how to parse this data and put it into a format or a structure that would make any sense. So that's what I kind of mean about this domain knowledge. Okay, so we have this. My goal is to make it better. Okay, so if we break out, so this is my source and target structure. So I have my source, which I just showed you. There's a concept column or a concept value column here under the concepts table in a relational database. And this is kind of my target data model. I'm just going to focus on one particular value, which is the 250 hertz frequency of an audiogram response. So I have 4 fields. So taking an ER diagram and changing it into more of these components that I spoke of, you can kind of get a sense of everything that I'm working with and kind of the scope of these things. So I have the high-level table of concepts, audiogram result, and then the individual fields. So the next part to this is formalizing relationships. So we saw the ER diagram, we see these components, let's formalize these relationships. So there's actually 2 kinds of relationships that I want to express here. The first is the structural relationship. So the fact that the concept value field, that component descends the concepts table, and so on and so forth for the other side. The second aspect is that when doing ETL, you're transforming data. You're turning it, restructuring it, parsing it, cleaning it, all that kind of stuff. And so just to keep it simple, I'm just simply saying that those 4 columns, individual fields, are being derived from that concept value column. So the second piece that I was thinking about was saying, okay, well, I have this structure, but what does it actually mean? What does it actually represent? And so what you have is actually 3 different resources that you can think about here. So the one on the left, up top left, is obviously kind of the raw source data. That's just kind of what it is, as it is. The right-hand side is the target. It's represented. It can stand alone. The third one on the bottom that kind of encapsulates these derived from relationships is actually the ETL process, if you want to think of it that way. That is the relationships between these 2 individual resources and how they are related together. So that's great, but like I said, things change all the time. So how do we handle this change? So the one approach that I'm discussing here, aside from just playing with images, is that all of these are being derived from the underlying metadata, the systems themselves. So I actually have 2 relational databases, and I'm extracting the metadata about the structure of those tables and columns. And so we can use the metadata as kind of an indicator to change. So if you query the database and you say, just give me all the metadata about these tables and columns. So you can understand that more if you kind of think about metadata in this context. So you might have the data types, you might have the structure of the data, and the relationships between these things. And so if we look at this, kind of boil it down to just taking one column on the right-hand side, we can see that these kind of form a dependency tree here, right? So we're saying this thing relies on this thing. Well, if we change the thing that F250 depends on, what happens? So the underlying thing changed. I said I derive from it. Well, this underlying value now changed. What happens to all of its dependents? And so we have a question, and we say, okay, well, we can do one of 2 things. We can assert that nothing has changed and we're fine, or we can say that, yes, the underlying thing changed enough that I need to maybe reestablish this link between this source and target data. And so this is where data provenance comes in. So data provenance is defined, this is defined by W3C. They actually have a data provenance specification, a whole family of documents that they've formalized. And it's really just everything that involves touching some kind of entity. So there's activities, there's people involved, there's actions, all those kinds of things. And the reason that it's compelling for this case is because it really increases kind of the trustworthiness of your data. You can understand the quality better because you can see how something came to be. We have all these source systems, we have this black box, and then we have output. But what happens in that black box matters to a lot of researchers and a lot of clinicians when all of their papers, all of their research depends on the fact that I did my job well and I was diligent with how I did this ETL. If all I have is a script that has all this encoded knowledge in my script, in comments, in SQL queries, and all that kind of stuff, that is not something that I can say, here, just trust me on this. You can read my script, learn how to program in the meantime. That's just not going to happen. So transparency of this through the use of data provenance is kind of a big deal. So as a result of this, I decided it would be a neat idea to use data provenance as a data model. All right, so let's get into the implementation. So this is a library, very young project, but it's called Origins. And for those who can kind of infer what the meaning of that means, so Origins is a Python library. It supports currently 12 backends. So a backend is something that it can connect to, such as a relational database. It connects to CSV files. It connects to a file system, tree structure. It connects to MongoDB and other various things. And what it does is effectively extracts metadata and the structure from those backends and represents it as a graph. And so you can use this programmatically, which I'll demonstrate in a second. But the other thing, because it's a graph, in fact, it's a hierarchy, it's a tree, it fits really nicely in a graph database. So I use Neo4j as the backend persistence layer for this. If you want persistence, if you want to be able to track this thing over time as it changes, this is a great database to do that with. And as I mentioned, I wanted to use Provenance as kind of a very integrated approach. So I actually use the Provenance, the ProvDM specification on the W3C. They define a data model. They define all of the things about Provenance and how it should be expressed. And that is very much integrated into this data model. Okay, so let's take a look at some things. So this is an example of just a quick code example of connecting to a SQLite database. So it's quite simple. You just import origins, and you specify the backend you're connecting to. So SQLite, that's great. You specify the path since it's a file in this case, and you connect to it. And what you get back is basically just an object, and it represents the database that you just connected to. All of these levels of the hierarchy, such as the database, tables, and columns, have properties. Some have more than others, and these backends have been written to kind of be somewhat pragmatic. It doesn't go crazy in trying to put everything known to man into these properties, but the nice thing is that the backends are relatively easy to write, and so if you have a kind of different requirement, you just write a backend or extend one of these backends, and you can automatically extract different properties. The other thing is that those properties are mutable, so you can change it after the fact. So if you don't want to write a backend, but you want to add more information to these components, you can. So I wrote this. This was the first part that I wrote because I wanted to just prove to myself that I could connect to these things and I could represent it in a way that was pretty general across all of these different resources, all of these different systems. And so being an object-oriented approach, you can access the tables of that database. And so for every backend, it uses the terminologies that are obvious to those backends, and you'll see what I mean in a second. So you have database.db.tables, you see all the tables. That's great. Those are table objects. You access the employee table here, And you can see that you just have the name of it. That's not very exciting, but then you can access all those columns. And then you can access the properties. And these properties here are extracted from the SQLite metadata table. It's a hidden master table in the SQLite engine. So that's SQLite. That's cool. So let's look at delimited files, CSV. So CSV is another example. You connect to a file or read in a file, and you get certain properties. In this case, I just represent it as a table because it's CSV, it's structured, and it's not very interesting, but you get the name of that column and the index, the position that you have. Here's one for MongoDB, and MongoDB is interesting because for those who have worked with MongoDB, MongoDB doesn't support like schemas. It has a database. You can create collections within the database, but the documents that you can put in collections can be heterogeneous. There's no requirement that you have to maintain the same set of fields in the document across documents. It's usually good practice to do that, but it doesn't mean you have to. You're not constrained to that. And so MongoDB has a whole host of properties you can extract about the database itself. They may or may not be useful at this stage, but they're there. So I just kind of threw them in there. You can access all the collections in that database. And what's unique about the indexer of MongoDB is that I actually also calculate the occurrence of a field that exists in that particular collection. So the only way that you can actually gather all of the unique fields in a collection is doing a MapReduce job within the collection. And so that's what it does. And it calculates the frequency or the occurrence of that field within that collection. So that was just something fun. But again, that might be useful to you. If you have this collection and you would just want to see what's the occurrence of these fields because that matters, that might be useful to you. So sorry about that, echo. So let's talk about the export to the graph database. So the programmatic API, object-oriented API is great. That's super. But the real power comes when you actually can persist this data and change it over time and see how it changes over time. And so what we have is same approach. You connect to the database, and then you can just call this function or this method export. And it actually exports a normal JSON serializable data structure. And this was very much intentional to create an intermediate format that does not depend on any of the backend APIs to be able to pump data into the graph. So if you have another means of generating this structure, which is very simple to make, you can still make use of the whole graph API of origins. So that was a deliberate thing. So you can kind of see that you have a key here. These are all the components that are being extracted. And then way down here are relationships. So relationships include such as foreign key references, right? It extracts those. So you have the structure, and as well as the definitions of the actual structure, so the hierarchy itself. Okay, so just to show you that every object you can export at any level, so you can export the entire database, you can export an individual table, you can export an individual column. So all of these objects support this method. So Origins also comes with a REST API. I'm a web application developer by background. I like building, I've chosen web as my platform, and I like it. And so I wrote a little REST API to query this graph when this data is in here, so you can get the data back out. And so it encapsulates a bunch of, for Neo4j, Cypher queries. So Cypher is a declarative language just like SQL, and you can query the graph, get data back out. So it basically encapsulates a whole host of Cypher queries. And so you can kind of see this is the root endpoint. You can access various things. I also wrote a client, a dashboard for kind of browsing around this graph in a non-graph kind of way. That's a little bit easier to consume if you're not going to be looking at an unwieldy graph in a visualization. So this is very much kind of a way to dig into resources, components, and kind of see what you have. So in this case, I have a few resources that I've exported or imported into the graph. In this case, you can kind of see the breakdown of components. So you can see that this particular resource is composed of one database, has several schema and tables and columns and things like that. So I'm not going to get into too much detail about that. What I would like to show, though, is that we have, from the example before, with that 250 hertz frequency, I imported that data. This is a component. This is a simple view. This client is very much a work in progress, so don't judge it too much right now. But we have kind of all of the information that we know about this field. And you can see that you can track the sources of these fields, right? You can track the sources of these components, where these things came from. And this is where the provenance comes in. This is where kind of you can express lineage in these across these components. So if I were to click into it, I just have a separate tab open here. You can see that when I integrated data from another institution, I was able to express this by creating a new resource that represented, in this case, Vanderbilt University's data, audiology data that they provided us. They have a completely separate data model that I had to perform ETL on, but I was able to represent their sets of columns and fields as components that I can then tie together with what I have now. And so you can see that this particular column there's a Postgres database, has sources of data derived from my nice, lovely concept value that is the CHOP data, as well as columns and data from Vanderbilt. And so you can create this graph that looks like something like this. If I can get a better view of it, that's not chopped off. So you can see that we have kind of this node up here, and here's like a whole host of metadata that was extracted from it. And you can see how things were derived. So this is part of the Provenance data model. You can see that this thing was derived from this thing was derived from concept value. Here are other columns. These are all these flags that I spoke about, like the masking flag. And you can see that this data was derived from that as well. And so you have this structure, you have this tree to be able to represent these relationships. And the lovely thing about graphs is that relationships are just as important as the entities themselves. The connections, the relationships between them are very important. So this is not just kind of out of the blue. Well, it kind of was, because I actually came across these two things I'm going to show you after the fact, but it was nice validation. So one thing I'll just kind of point out that for people not in healthcare, not in kind of dealing with metadata and all this kind of domain knowledge stuff, if you're just a general web application developer like how I am, and you're consuming all of these APIs that are exposed on the web all the time, you have to deal with change all the time. Your clients are going to break. If you're not keeping up with blog posts and things like that, your stuff is going to break. You have to be able to respond to that. And you may not be able to go back and say what changed in the past. You might be able to go back and look at blog posts, but there's really no structure that's available that's actually accessible to you. So Facebook has a 90-day breaking change policy. I'm not criticizing any of these. I'm just kind of proving a point that things change, and they put these policies in place because things change. Twitter had a 6-month migration from 1.0 to 1.1. Google has a 1-year deprecation policy. So Google Analytics is one of the Google services that is probably always going to stay in place. And they realize, because of its use, that they're going to publish a metadata API, and which enables clients to be able to consume this and say, here's all the things that I can be able to look at in my analytic data right now. And you can see that there's kind of a similar structure here. You have kind of the properties about that particular field. You have identifiers. And the notable thing is that there's a status field there. There's a status field in those documents. you can see the second one says deprecated. So that is a way that they help inform the user of when their fields are deprecated. And so clients can still use that as data rather than just removing it as a whole and being able to adjust their clients. This is another interesting one I came across. This actually is a text-based approach, but this is called API changelog.com. And they actually index documentation web pages from a whole host of services. And what they do is they simply run a background like cron job or something, scrape the metadata, and then diff it with the previous time that they scraped it. And you can actually see changes and get notifications of changes. And that is kind of a big feature that is going to be part of the origins graph and the application as a whole in the future. And so this is something that, oh, look, there's 2 new get parameters that I can use in order to query this data. So just to kind of wrap up here, this graph really kind of hit me hard when thinking about this and how to make my life easier as a developer in this complex domain. And these are kind of the 3 main topics or 3 main goals of this project. But I'm curious if anybody else has any ideas that stemmed from this talk. But these are kind of the 3 main things that I'm going to be focusing on as I work on this. And I would like to say thank you for listening to me. So just some information. The top link is the project itself. Again, it's very early development, but there are some documentation that's being updated regularly. There's also a Google group for discussions, and that is my contact information. Any questions? Yes, sir. Search? Yeah, so the in terms of like searching the properties and things like that. Yeah, so there's so Origins kind of defines some few kind of base properties for that purpose. You have the identifier. It establishes a UUID because I have some future thought that if you have separate Origins graphs, you can still cross-reference them by UUID or URLs or something like that. But it has like a label description as kind of a base free text way to search the data. But then there is planned support for the client to be able to search in the actual properties themselves. So right now it does do free text searching on the description and labels of those to find them across the entire graph. But eventually there's going to be support for searching by individual property also. Yep.
What you explained there has an immense amount of metadata.
Yeah.
Stuff about each table, stuff about each field.
Yep.
And also the provenance of those things.
Yes.
You're putting those in by hand? Or
No. So there's
extract the provenance of a piece of data out of a database.
right. So the question is how am I representing that provenance data? So the amount that Origins can infer, the amount of provenance that Origins can infer is like very minimal because of that fact. Like I don't know when the person who actually created the database column in the relational database or something, or the table, I don't actually know when they did that. I can't infer that because you just happen to pump it into this graph. That doesn't jive well. What it does do though is when you do the updates and you basically you can do a synchronization of an export from the database, let's say, compare it with the current state in the graph, and then determine if things have been added, changed, removed, whatever. So it's able to track revisions, and that's kind of the main thing that it's able to do right now. But because it's built on top of the ProvDM data model, you can actually there's a prov JSON format that you can actually upload and target one of these components and just tack on a whole host of other provenance data about it, such as the activities involved, the agents, all that kind of stuff.
The W3C
Yeah. Yep. Yeah, that's like a whole separate talk, frankly, so that's why I didn't go into it too much, but it's really built on top of that. So, okay, I think I'm out of time. Is there one last question at all? Cool. Thank you very much.